All right, so we've seen how to estimate the regression line. And what it was to give me an estimate of the slope, of the intercept and of the slope when you regress head circumference on gestational age. And here it is, I've drawn it, and without the jitters, so you can see that why we did the jittering. All right, so that's the estimated regression line. That works fine, that works terrific if you've got linear regression. Okay, what if the regression is not linear? What can we do about that? Now, I could be flip and say, come back for the next course where we look at nonlinear regression. But without being flip, there are sometimes what we can do is, you know, like if you only have a hammer, anything looks like a nail, and you try the same sort of idea. You maybe will take a look at this nonlinear relationship. Maybe you can sort of straighten it out so that it looks linear and then do your things. So there are some situations where we start off with something that's not linear, but we can linearize by doing a transformation. So here is the stuff jittered, and you can see that the regression line looks pretty good. Now, what we can do to reinforce this belief that the regression line was pretty good and also evaluate what our assumption of homoscedasticity meant, we can look at the residuals. And here they are, and they're horizontally, and it looks like the variance or the standard deviation, it looks like this doesn't seem to vary too much with gestational age. There are a couple of points out here that are a little problematic, but apart from that, it looks like our assumption of homoscedasticity was fine. Our assumption of linearity was fine. There's no shape left in these. They look pretty flat, and so we seem to be okay. Now, what we can do is we can also put a regression. We can also put a confidence curve around the line. Okay, and what this is so the line gives us the mean. So that gives us the mean, and what we can do is put up a confidence interval around which the mean, 95% we're 95% confident about this interval covering the mean, the true mean. Okay, and that's that interval there. We see that the interval seems to be tighter near the center than it is on the extremities, and that sort of makes sense because most of our data are near the center, and so that's where we've got most of our information. But there it is. That's the, we can come up with a confidence interval that way. Now, that's not the same as asking where the observations will lie. So here, this one tells us where the mean of that curve will lie. So if we're looking at the mean of all babies who are 25 weeks gestational age, where does the mean of the head circumference lie? And that's what that is referring to. Whereas if you ask me where 95% of the babies' head circumferences are for babies who are 25 weeks, then I have to give you a broader interval, and that's what this one is. So this is the regression line plus prediction intervals. So this is where we expect 95%. For any given gestational age, this is where we expect to see 95% of the kids. So what's our general strategy for regression? We can draw a scatter plot of the data. That gives us an idea of how the relationship should be and whether we have, in fact, linearity or not. Then check the residuals. So plot the residuals versus fitted Y's, and there should be no discernible pattern. You shouldn't have something fluting out like this, which says on the extremities the residuals are much more variable than they are in the middle. You shouldn't have that. You shouldn't have any discernible patterns. You shouldn't have the residuals going up like this. You shouldn't have the residuals on some sort of curve. They should be just all over the place, the same as they are here. Okay? That's what we expect to see. So here is what we hope not to see. So here is a plot of birth rate. So this is birth rate for some countries, and this is the GNP, the gross national product for those countries, per capita GNP in US dollars. And it looks like the relationship sort of looks something like that. It's certainly not linear. Okay. So what can we do about this? Well, as I said, there are some times when we can do something about this, and we think about it a little bit, and we think about this as follows. Now, if we look at plots of y equals xp for some positive p. So for example, if you look at the plot of y equals x squared. So this one here at the bottom is y equals x squared. It sort of goes up. As x becomes bigger, the curve goes up. It's even more pronounced when we look at p cubed. And this is only because of the scale that it looks like, the p squared is much lower. Now, what would you do? So for example, if you had this thing p cubed, and you had this curve here, you got this curvature, how could you get rid of that? Well, if you've got y equals x to the p, then we can, if we looked at 1 over p of that, so if we, instead of x to the p, we call it, if we look at the pth root, so if we reverse, if we plot y against this, we would get a straight line. If we slowed x down, so as not to increase as x cubed, but rather to increase at a 1/3 root of that speed, we would straighten things out. And we would have to do more if it's p equals 5, we would have to straighten it out even more. So this is one idea. If the curvature is this way, then what we would do is take the root of the the root of the transformation, and that should straighten things out. What about the other direction? Well, if we look at the relationship when p equals 1 over the square root, so for example, if we have the inverse square law, then this is what happens. We would get this kind of picture. So here it is for p equals -1, so 1 over x, and so on. This is p minus the square root, 1 over the square root. Now, instead of putting p equals 0, which would be a straight line, I've slipped in, and what we do is the p equals 0 is the same as taking the logarithm. So let's just take the logarithm. And the reason I'm doing this is because if we do that, then we can create what is called a ladder. So here's the ladder, and here's the ladder in terms of the y's. So we go from -2 to -1 to -0.5. This would be the 0, but let's just do log, and then go up the ladder, 0.5, 1, 2, and we can use any numbers. This is not restricted to -2, -1, -0.5. It's any number, any negative number. But what we do is we make the negative number smaller or bigger, whatever you want to call it, by going in this direction, and then by going in this direction, we make the p positive and larger, and by going in this direction, we make the p negative and smaller. So going up the ladder, we call this going up the ladder, going to the right, and we call it going down the ladder when we go to the left. So if we do a scatter plot and end up with something that looks like this, which isn't linear, okay, but we can argue that this is sort of like this. Okay, so let me draw that again. So this is sort of like that. It's not linear. Then what we might be able to do is, you see, that sort of looks like this. Okay, and so what we might be able to do is take advantage of a transformation like this and see if that straightens it out for us. All right, so for example, go up and down the ladder, either on the x or the y, until you reach something that looks kind of straight line. And here is a guide. So the guide is this. Think of the 4 quadrants. Now, if you've got this kind of shape, we call that a quadrant 1. If you've got this kind of a shape, we call that a quadrant 4. If you've got this kind of shape, then in your scatter plot, we call that quadrant 3. If you've got this kind of shape, we call that quadrant 2. If you are in quadrant 1, try these transformations. Namely, you either go y, make y go up the ladder. So you might look at y squared, or you might look at y cubed, or y to the 4th, etc. And then replot. Or let x go up the ladder and see if that straightens up. So x starts off at 0, p to the 0, and then you might want x squared or x to the 1.5, or even you might even start off with the square root of x. I'm sorry. So start off with square root of x, or maybe x squared and so on, and go up the ladder. If you've got a shape that looks like this, then you have y going up or x going down. Should help you straighten it out. If you've got this, then you've got y going down or x going down to straighten you up, and so on. So there are your 4 quadrants. In fact, if we looked at the logarithm, if we looked at the logarithm of GNP, so we look at the birth rate versus the logarithm of GNP, we get something that now looks much more linear. And we've linearized it. So this is one way of getting around non-linearities, but basically it works only when you've got something that's nicely behaved like this. And so that's how it worked in this one.